the end of last lecture, we got to the point of believing in this function. That is, I showed that if I have a continuous function from z cross x to y, then the map, which just gives that the parameterized family of partial functions, so it sends z to f z blank. We proved that was continuous. I have to say, the very end of that proof, I didn't say very clearly in the lecture. I've adjusted the lecture notes to make up the difference, so hopefully that's clear now. I don't want to revisit it exactly, because then I'll spend 10 minutes sort of setting up the first part of the proof again, which I think is maybe not the best use of our time. So this is where we got to at the end of last lecture. So now, taking that, that means this function is well defined, right? So out of an f, I get this thing on the right-hand side. The claim is that it's bijective, okay? And that's what we're going to discuss now. Well, let's get injectivity out of the way. That's clear. Because, let me just write psi for this thing. So we're going to fix z, x, and y. Injectivity has nothing to do with the compact, locally compact Hausdorff condition, right? So it's clear because if I had psi f equals psi g, well, I'm just remembering the data of f in a slightly different package. So certainly, if I have those psi's being the same, then f and g are the same, or more precisely, for z in z and x in x, well, I'd have f zx, that's equal to psi f. So psi f is something that takes a z. Psi f z is exactly that partial function f z blank. So if I feed in an x to psi of f of z, then I get f zx. And if psi f and psi g were the same, then that would be this, but that's gzx. Okay, so as I said, psi f and psi g, psi f is just repackaging the data of f. So f equals g. Okay, so the work here is to prove that it's surjective. Okay. Well, so we have to take a continuous map, let's say lowercase f. And we need to produce a capital F such that psi of capital F is lowercase f. Well, we don't have to try and figure out what capital F is, because there's only, it's determined by what lowercase f is, right? So if, that's this calculation. So if we had psi f equals lowercase f, then, well, f of zx would be psi of f of z of x, and if psi of capital F is lowercase f, that's f of z of x. Okay, so there's only one possible capital F that could work, and that's this one, right? So given lowercase f, we can define as a function capital F by this formula. If that were continuous, we'd be done, because by construction, psi of that thing is lowercase f. So that's the whole game, is to prove that this capital F is continuous. Okay, so if we can show this capital F is continuous, then psi of that, otherwise we can't really write down psi of it, right? It doesn't make sense because it doesn't live in the domain. But if capital F defined by that formula, which is a well-defined function from z cross x to y, if that f is continuous, it's in the domain of psi, I'm allowed to write this down, so maybe I'm saying out loud more than's written on the board, maybe. So, okay. So if psi of capital F is lowercase f, then it must be this. So let us define a function capital F from z cross x to y by this formula. Okay, I'm not assuming anything, just this is how I figured out that formula was correct. So I can define that function given lowercase f, and now I check that that's continuous, or the plan is to check that it's continuous. So if we can show it's continuous, then that's the case. So psi is surjective, and we're done. All right. So what do we know? We know that lowercase f is continuous, and we also know that for every z in z, f of z is a continuous map from x to y. Okay, that's the data we have to prove that capital. Right, so what does continuity of lowercase f say? Well, we know a sub-basis for the topology on the right-hand side, right, on this guy. A sub-basis for this, the topology, is these SKUs, right? K compact in X, U open in Y. That gives a sub-basis, and if I want to check a map is continuous, it's if and only if the pre-image of everything in the sub-basis is open. So the data of lowercase f being continuous is precisely the following information. It says that for K in X compact and U in Y open, the following set is open. Okay, so at the moment I'm just setting up what I know, and then we're going to try and use that to prove uppercase F given by that formula is continuous. So what's the set? Well, it's the pre-image under F of SKU. Right? That's a subset of Z, and it's open by continuity of lowercase f. What is that set? Well, it's the z's in Z, such that f of z, well, to say f of z is in there, remember that this SKU was precisely the set of all continuous functions which, when restricted to k, had image contained in U. As I mentioned last lecture, at the moment you're not supposed to have a very intuitive connection to this set. We're going to spend time on that later, but for the moment that's just what it is. Okay, so this says that fzk is in U for all k in k. Well, but that's fzk, capital F. Right? So that's z in Z, such that fzk is in U for all k in k. And, well, it'll be convenient to write that in the following way, which is that it's the same as all the z's in Z, such that Z cross k is contained in F inverse U. Okay, we saw something similar last lecture. Okay, so that's open. We know that's open. In Z, right? Okay, so I want to show for any U in Y open that F inverse U is open in Z cross X. Okay, I mean this, forget about that now. U is just an arbitrary open subset of Y. So we want to prove its pre-image is open. So that's what we're doing. So we're going to take an arbitrary element of the pre-image and show that it has an open neighborhood contained in the pre-image of U. And that'll suffice to show that the pre-image of U is open. Okay, so given a Z cross X in F inverse U, So we want to find an open neighborhood of Zx in F inverse U, and then that'll be a union of all those neighborhoods, therefore open. All right. Well, here's where we maybe think to use the other piece of information we have, namely that for every z, in particular for that z, the image of f, the image under f of z is a continuous map. Right, so z and x are now fixed. Right, but if I apply f to that particular z, I get a continuous map, and well, then I can take the pre-image under that map of u. Okay, it's clearly got something to do with this, right? So that's a reasonable thing to do. Okay, so the pre-image under that thing, so let's call that C sub z, which is, well, fz inverse of u, but that's a bit of a confusing thing to write, so let's write it out explicitly. So that's all the x's in x such that fz of x is contained in u. All right, so that's open. Well, x is a bad letter, isn't it? Because we've already used it, so let's use p. Okay, so well, another way to write that is that's all the p's in x such that capital F, z, well, such that z comma p is in F inverse u. Because that's just capital F, z comma p. To say it's in u is exactly to say that z comma p is in F inverse u. Okay, so that's open in x. All right, and well, I mean, this particular x that came in our pair belongs to C sub z by hypothesis, right? Okay, so that's an open neighborhood of x in capital X. Okay, so far we didn't really do anything, we just wrote down what we know. Now is when we have to actually start thinking. Any questions up to here? Okay. So we assumed that X was locally Hausdorff. Sorry, locally compact Hausdorff. So that means we can do the following thing. So since X is locally compact Hausdorff, and we proved last time that such a space is regular, so remember, regular meant I could separate a point from any closed set not containing the point by open neighborhoods. Okay, so my closed set is CZ complement, and my point is, well, obviously X. Okay, so there's X. Here's CZ. There's X. Okay, so applying regularity to the pair X comma CZ complement, we obtain disjoint open sets. What am I calling them? W1, W2 with X in W1 and CZ complement in W2. to say CZ complement is contained in W2 is just to say that W2 complement is contained in CZ, right? So I can draw these open neighborhoods as follows. So there's W1, and well, W2 contains everything not in CZ and perhaps a little more, right? So it looks like that, where everything outside this circle is in W2. Okay, so this is the situation. All right, so there's a closed set, namely W2 complement. Well, X is not in W2 because X is in W1 and W1 and W2 are disjoint. So X must be in the complement of W2, and I'm calling that K. I mean, the K wants to stand for compact. I don't know that because the space is not, I mean, in a compact Hausdorff space, any closed subspace is compact, but it's only locally compact. So the K is suggestive. I'm going to shrink it in a minute to make it compact. But this is a compact set containing X. Why do I care about getting a compact set? Well, because of this, right? I mean, the only thing I know about the topology on the space of continuous functions is this to do with open sets and compact sets. So I need to get myself a compact set somehow. All right. So that's true. And X is in W1, which is, well, contained in the complement of W2. Right? That's again just because W1 and W2 are disjoint. Okay, so now I use that X is locally compact. So what does that mean? It means there's an open neighborhood of X contained in a compact subset of X. So open and compact in X, right? I won't write that. Such that X is in T is contained in L. Okay, so that's a lot of letters on the board. I appreciate that. So the important ingredients are W1 and W2 complement. I'm just using this T and L to shrink those down. So that's why I'm not going to draw pictures for them. So we set K tilde to be L intersect K. Okay, so I claim this. I mean, I said I wanted to think of K as compact, and it's not, but I'm going to shrink it so it is. So that's what I've just done. I intersected it with something compact. Why does that result in something compact? Well, L is compact and K is closed in X. So intersecting L with K gives me a closed subspace of L in the subspace topology on L, and therefore it's compact. All right. So K tilde is compact. And, well, X is in L, and it's also in K. So X is in K tilde. And moreover, the important point is that this is true. Okay. Also, why is that? Well, I mean, I need to justify these two inclusions. That one is just what I just said, right? So that's clear. Why is it the case that Z cross K tilde is contained in F inverse U? Well, we come back to CZ, right? So what's CZ? CZ is the set of all points in X such that Z taken with that point lies in F inverse U. So for this to be true, I'd only have to know that K tilde is contained in CZ. Well, so why is that? So K is contained in CZ, and K tilde is a subset of K. So right. So by definition of CZ, I've got this. Well, that's now looking like something I can use, right? W1 I just intersect with this open set T. And by construction, it's still an open neighborhood of X in X. Well, now it's an open neighborhood in K tilde, right? Because T is contained in both L and right, is that true? Yeah. So T is contained in L, and W1 is contained in K, right? So why is it the case that W1 tilde is contained in K tilde? Yeah. So W1 is contained in K, and T is contained in L, so therefore W1 intersect T is contained in K intersect L, which is K tilde. All right, so this thing is contained, this intersection W1 tilde is contained in K tilde. All right, well, so now we're in a position to do this. Okay, so what does this say? It says for any compact subset of X, say K tilde, and for any open subset of Y, I get that this is an open set. Okay, so let me write down what that set is in this for K tilde and for U. So it's those W's in Z such that W cross K tilde is contained in F inverse U. Okay, so let's just agree locally it's correct, and I'll explain what I'm doing. So K tilde compact U open, so that set is open in Z. All right, so that set is this. I mean, forget about the Z's there, that was a variable. There's no particular connection to the Z that I ended up with in that pair. That's just something ranging over Z. All right, so that's open in Z. And then we're done, right? Because we've got Z comma X is contained in V cross W1 tilde is contained in F inverse U. Right, this inclusion, well, Z is in W, why? So Z is in V, why? Well, V is the set of all elements of Z such that taking that element cross K tilde lies in F inverse U, but, well, you know, Z makes that work, so Z is in V, and X is in W1 tilde by construction, so you believe this. And, well, this here, I mean, well, so maybe. So why is this true? Well, take a pair. So take a V and, I don't know, a T in V cross W1 tilde. So by definition, then, since little v is in V, we have that little v cross K tilde is contained in F inverse U. But W1 tilde is contained in K tilde, so that means that V cross W1 tilde is contained in this, is contained in that. So by construction, that is also true. Okay, so I've constructed an open neighborhood of every point in inverse F inverse U, so that's open. Okay, it's not meant to seem easy. Right, so this is a non-trivial theorem. Okay, so how would you have arrived at that proof? Well, you write down what you know, and then you try and construct an open neighborhood of a point, and then you'll figure out that you need a compact and open set which have this kind of property. You'd need to sit this inside a compact set to make it work, so you'd need this, and then you'd work backwards to find the relevant kinds of neighborhoods of X and Z. Okay, so from that point of view it looks plausible, but it's a bit of an intricate business. Okay, any questions about the proof? All right. So that's it for the theorem. So we've got ourselves function spaces and the basic fact about them. So now let me go back and just remind you the consequences we derived from having this adjunction property, which are now fully fledged theorems. Okay, so corollary. So if X is locally compact Hausdorff, then the evaluation map is continuous. Right, so take a function from X to Y, take a point, send it to the value of the function on the point. Okay, so with the compact open topology, that's continuous. As I explained a few lectures ago, that's a consequence of this adjunction property, so I don't need to prove this. I explained how it follows from that property already. So that's important. And then we have some various other statements telling us that compositions are continuous. So if I have a continuous map and the target is locally compact Hausdorff, then for any Z this map is continuous. So this is what? Blank circle F. Okay, so taking a continuous map from Y to Z, precomposing with the continuous map F, gives me certainly a continuous map. That's not saying anything. We knew that already. Compositions of continuous maps are continuous. But that process is continuous as a function of the input. That's new information. And if I have a continuous map G, and X is locally compact Hausdorff, then the map which post-composes with G is continuous. Okay. So, I mean, without those facts, you basically can't do anything with function spaces, right? So these are the cornerstone of everything we're going to do with function spaces, and it's a consequence of this theorem that we know they're true. All right. Okay, so what's the problem we have now? Well, when we defined a topology and we're able to prove something about it, but I mean, it's still a bit mysterious at the moment how we're supposed to think about the open sets in that topology. What does it mean for two functions to be close in that topology, or more precisely, you know, if I had a sequence converging to a function within the topology that I've just defined, what does that mean? Yeah? I mean, you've heard of uniform convergence before, so is it related to uniform convergence? What's its relation to point-wise convergence? Well, those are all the natural questions that arise at this point. Okay, so we're going to do two things. So we're going to put, so in the case where X is compact and Y is metrizable, okay, this space is metrizable. Okay, so we'll prove this next time, but let me give the statement. So choose a metric on Y. Any metric. I'll get the same topology out at the end. Well, I can define a topology, sorry, I can define a metric by the following formula. Okay, so given two continuous maps from a compact space to a metric space, well, what do I know about the images of compact sets under continuous maps? I know they're compact. And since they land in a metric space, they're sequentially compact, and in particular, bounded. Right? So this makes sense, to take the supremum over all points okay, take all the f of x's and g of x's, take their distance in y. That will be a bounded above set because of the hypothesis that x is compact, and therefore I can take its supremum. And the claim is that that's a metric on CTS xy, whose associated topology is the topology we've just defined. Take a sequence of functions. What does it mean to say it converges in that topology? That's well defined, given our discussion of metric spaces and sequences. It would mean that for every epsilon, I can find an n past which the sequence, this distance is less than epsilon. Well, that is to say, the distance in y between f of x and g of x is less than epsilon for all x. That's uniform convergence. Okay? So at least when x is compact, what we've captured with the compact open topology is precisely uniform convergence. So that's also worth knowing. Now, the reason I didn't sort of present the metric first is that, well, it's clearly not the fundamental thing, because any metric on y gives rise to the same topology on CTSY. It gives you a different metric, however. Okay, so there's many metrics you can choose on y. They'll all give different metrics on the function space, but the underlying topology is independent of all of that. One way of proving it's independent is to have set it up prior in some other way, and then to have proved that any particular metric gives rise to that fundamental underlying topology. Okay, so that's what we'll do next time. We'll also sort of discuss maybe another way of thinking about the compact open topology in terms of graphs. So let me just briefly explain. So if I take x and y actually compact Hausdorff, x cross y is compact Hausdorff. The set of closed subsets of x cross y has a natural topology. It's a bit odd, okay? But that's true. So the set of closed subsets of x cross y has a topology. I can send any f to its graph. That's a closed subset. And actually, that is an embedding. So this map identifies CTSXY homeomorphically with its image. So in that sense, you can think about functions as being graphs, and the neighborhoods of a function are just neighborhoods of the graph. Okay, so conceptually that makes precise what I said at the beginning of last lecture when I drew this square and then sort of said that's how you'd want to think about neighborhoods. That's actually a theorem. Okay, but we'll do this first. Okay, so let's take a sort of easy case for this. I mean, we have this topological space now, but let's take a sort of very simple case and see if we can understand it some different way. So just take X to be a finite discrete space. All right, so what does CTS XY look like? Well, I mean, if you've got the discrete topology, every subset is open, so every function out of this set to y is continuous, so there's no distinction between this and just the set of all functions from 1 dot 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 n to y, but that's just n copies of y. Right? So as a set, that's the same thing, and then the claim is that this is actually a homeomorphism. Which is to say that the compact open topology there is precisely the product topology on that product of y with itself n times. Well, why is that? I mean, what is the sub-basis for the topology here? It's these SKUs, right? So I take any compact subset of X, well, that's just any subset. So I take any subset of X, and I take U and Y open. I mean, the SKUs, if I intersect them, I'll get, so I might as well just take K to be a singleton. That's a general case. Right, because, well, I mean, think about SK1U intersect SK2U in general, I mean, for any X and Y. So what's that? That's the set of all functions from X to Y, which have the property that fk1 is contained in U, and also that fk2 is contained in U. But that's just saying that the union is contained. Rather, the image of the union. So that's just sk1 union K2 U. I mean, unions of compact subsets are compact, so that's a valid thing. All right, so that is why I can just write a singleton there, because if I took SKU for K finite but not a singleton, it would just be, you know, an intersection of a bunch of the things where there's singletons. So this is also a sub-basis if I just take singletons. So what is this subset? Well, it's all those functions from X to Y such that Fi is in U. Well, what does that say? I mean, what's the correspondence between this and this? It's I take a function and I send it to the tuple, which just does this. Right? That's the image of a function. So if I say that the image of I is contained in U and there's no other constraint on F, that's just to say that I took Y and then in the ith spot I stuck a U and everything else was just all of Y, and that's an open set in the product topology, as I know, and that's the corresponding, I mean, I'm just making this identification, but actually what I mean more precisely is that this subset, the image in the product, is this. Okay, but we know that that's a sub-basis, as I've written it, for the topology on the product space. So that shows you that the topologies here are the same. Okay, so the finite product spaces are just special cases of the compact open topology. It's not true for infinite products, okay? So be careful about that. All right. Well, okay, so we know if Y is a metric space, then the product of Y with itself a bunch of times is a metric space. Well, maybe we never officially did that, but you did it with Rn if you think about it, because that's what the D1 metric is. Right? The D1 metric takes the metric on R, which is just the absolute value, and says the distance between 2 points in Rn is you just add up all the D1 distances between all their coordinates. So that works in general. It's the same check. Right, so the distance between y1 up to yn and y1 prime up to yn prime. So I can define a metric on the product of y with itself n times to just be the sum of all those distances. Okay, well that means, that's a metric and it induces the topology, the product topology, as you can check. So that means that at least in the case where x is finite and discrete, well, we already knew, and y is a metric space, we knew how to think about this topology as arising from a metric, that is, it's metrizable, and therefore this is metrizable. Okay, so, however, the step to here isn't quite trivial, because, well, there's a sum there, right? So, that actually generalizes in a different direction. That would be asking for an integral. If I try to generalize that from x finite and discrete, well, that's a compact space. I could ask what happens when I take x to be not finite, but compact, which is the sort of closest I can get to something being sort of finite. So if x were compact, not necessarily finite, and y was metrizable, well, we might like to write down a metric on this set of continuous maps from x to y by some formula which just replaces the sum by an integral, right? So you could say the distance between f and g, you could say that equals the integral over x of the distance between f of x and g of x. And that's what that is, right? Because, these tuples are really functions. They're functions assigning to, each index some element of y, and the distance between them was just adding up, indexed over all the things that were in the base, that is the indices for which I'm taking coordinates, adding up all the distances. So that's the natural generalization. That needs, in principle, us to know how to integrate things. In general, it needs some sort of measure on x. Well, it doesn't have to. You know how to define integrals on this or Cartesian products of that with itself, and then that would actually work. So, okay, so if x is that kind of compact space, that would be a plausible generalization of that, and that works. That gives a metric, as we'll check. However, so if x has a measure on it, then we can try that. That will also work, and will give the same topology as the compact open topology. But without anything, without any measure, without any notion of integration, we can write down the supremum, right? And that would have been an alternative definition here, right? I could have, instead of writing the sum, I could have written the supremum over all these that would have been another metric on the product, which would have induced the same topology, namely the product topology. Okay, so this potential definition, in this special case, generalizes to any compact space, no other conditions necessary. This requires a theory of integration, and well, both are useful, and we'll discuss both. But this one we'll start with because it's defined all the time. And okay, so I think I'll stop there.